So thank you, Alejandro Monreal, for presenting today about spiral fMRI, specifically spiral fMRI VASO at 7 Tesla, and then also spiral fMRI BOLD at 9.4, and the first sub-millimeter fMRI at 11.7 Tesla. So Alejandro has recently joined the Martino Center to work as a postdoc for Rob Frost on motion correction in the group of LTN from Bruce Fischler. And you did your PhD with Ben Poser in Maastricht. Yes. Please try sharing your screen.
Yes, exactly. Thank you, Renzo, for the introduction. Right, sorry.
Feel better now that I live about so it's
There you go. Can you guys see the screen?
Yes, that works.
Okay, perfect. Well, thank you, Renzo, again for inviting me to present some of my results with spiral for fMRI, spiral readouts. And yeah, well, Renzo already introduced myself. I'm Alejandro Monreal Madrigal. I was working with Ben Poser in Maastricht, and like a month and a half ago, I moved here to Boston. Today, I'm mostly going to be talking about my PhD project, which is on 3D stack of spirals readouts for high-resolution fMRI at ultra-high fields. Here, just a little bit of an introduction about the project I was part of, which is the Aroma project. We were 6 different partners working on developing the tools for the 11.7 Tesla scanner that is in Paris. Maastricht University, we were developing the fMRI sequences. DCNE in Germany was mostly working on anatomical sequences. ETH in Zurich was responsible for motion correction techniques. Scope, of course, they were providing the field camera. University of Glasgow developed the RF foils, and SIA, which is Neurospin, where the 11.7 Tesla is installed. They were managing the project and yeah, well, doing many more things probably. This is just a small example that I took from the paper they published some years ago, where they were trying to again show the benefits of going to this type of field strengths. In this specific case, they try to match the contrast in these 3 different field strengths, and they fix the acquisition time to 4 minutes and 17 seconds. And they played with the different parameters to manage to get a similar CNR. And with these 2 constraints, they were able to do 0.5 isotropic, 0.5 in-plane resolution at 3 Tesla, 0.32 at 7 Tesla, and 11.7 Tesla at 0.2 millimeters. So yeah, well, this is just an example, a way they managed to compare these different field strengths. And of course, we can see that with 11.7 Tesla, in just under a bit after more than 4 minutes, they were able to get these nice 0.2 millimeter images. So okay, that was a bit of an introduction of the project, and now I will dive a bit more into spiral readouts, which I heard some of you guys in the audience have some experience with this. This is on the left, we can see a typical spiral K-space trajectory, where it looks different than the typical EPI. In this case, we can transverse this K-space starting from the center of the K-space and spiral out, going outside. And we can do this in a single shot matter. So in this case, we start from the center and we move outside of the K-space in a single shot. These are parameters represented. I simulated this data for a field of view of 140 by 140 in plane, and with an in plane undersampling of 3 with a nominal resolution of 1 millimeter. So in this case, if we do single shot spiral out, we can have a very short echo time of 2 milliseconds. And in this case, the readout will be 35 milliseconds. We can cover the same K-space area, but now starting from the outside of the K-space and moving inside in what we can call the single shot spiral in case. In this case, the echo time is around 35 milliseconds, and the readout time is also 35 milliseconds. We could also segment our readouts to cover a similar K-space area. In this case, we can see an example of 2 shots. So we can call this dual shot spiral out. And once again, if we start from the center and we move outside, we can have, again, the very short echo time of 2 milliseconds. And in this case, a readout of 18 milliseconds. And once again, we can move from outside of the K-space and go inside, and we will end up with an echo time of 18 milliseconds. These examples, these images I showed before were in the 2D plane, but we can then stack each of these 2D planes in the partition direction, and we arrive at what we call a stack of spirals. So the motivation of my work is, I'll try to start with why ultra-high field. As most of you probably already know, it can give us a nearly quadratic increase in SNR. But of course, this comes with some limitations, such as B0 and B1 inhomogeneities. Why did I choose to look at spiral readouts when we all know EPI works very good? You can get decent images, very good images, like everything is fine. Well, spiral readouts are supposed to be an efficient ways to transfer or cover the K-space or sample the K-space. As I already showed before, it gives us a bit of flexibility on choosing the echo time, especially if we do spiral out, and we can do shorter echo times. And also something important is that it gives us a favorable G factor. So normally the G factor values are lower with spiral, and the pattern, the noise amplification pattern of the G factors look different than the EPI. But 2 of the main limitations of spirals is that we can get blurring in the image domain that we need to correct for. And also the reconstruction times are typically longer and have to be done offline. For the sequence development, I started using PulseSec. And the main reasoning is that, as you probably also know, is a vendor agnostic way of programming the scanner. So basically you can program your sequence in Python or in MATLAB, and then you can run the sequence at the scanner. But one of the main limitations is that most of the parameters are fixed at the scanner. So you program everything else, all the parameters such as resolution, field of view, everything, the undersampling factor, all your spiral readout, you program it in MATLAB, and then at the scanner, you cannot modify these parameters. However, you can change the slice positioning, you can tilt it, so at least you can place your slab as you would like to. For the reconstruction, I also made use of this open source software. It's a Julia package that is called MRI Reco. And one important benefit of MRI Reco is that it has some efficient or fast implementation of the NUFFT. But once again, at least with the setup I have at the moment, this reconstruction of the reconstruction of these high resolution spiral images has to be done offline. So with this, I can come to the goals of my project, which was to provide a flexible pipeline, including the vendor agnostic sequence and open source reconstruction. And also importantly, to explore the possible benefits of using spiral acquisition for high resolution fMRI at very high fields. Here in this slide, I just want to show a little bit of an example on what the difference are between spirals and readouts, spiral readouts and EPI readouts. And as you know, in the top, we have a typical EPI readout, and we can make use of the FFT, and we can arrive at an image that looks similar to this. And as I mentioned before, with spiral, since it doesn't fall into a Cartesian grid, we need to make use of the more computationally expensive NUFFT, or non-uniform fast Fourier transform, and we arrive at something like this. These are just example figures, but we can do a bit of different things. One of the main differences with the spiral is that since we are not using only one phase encoding gradient, as we do in EPI, we don't get that typical distortion in the phase encoding direction that we would get with EPI. But of course, that means that in spiral, instead of getting this distortion, you get the distortions everywhere, and that produces some blur. That's one of the reasons why you can probably see that the bottom image, the spiral image, is a bit more blurry, and it seems to have a lower effective resolution than the EPI one. Additionally, you can see a bit more of resonance artifacts, especially here at the edge of the brain. And this is just an example to also show how spiral readouts are in generally more susceptible to B-naught inhomogeneities. And that's the reason why we do need to work for them, as I will show in the following slides. In the right, we see some examples from G-factor maps, where in the top row, the spiral images show lower G-factor maps, and also they are more spread out. So in general, we won't have some spots in the brain that has a lot of noise amplification. So this is also another benefit of using spirals. Here, a little bit more about the open source tools I used. PulseSec, as I mentioned before, is hardware independent, and we can program the sequence in MATLAB. Then we generate a pulse sequence file, which is like a text file that you can then bring into the scanner. And this file is going to be read by these different interpreters you might have, either a Siemens, GE, Bruker. Now, I believe there is also a Philips interpreter for PulseSec files. And this allows us normally to have a faster implementation of a sequence. So it's also very good for prototyping. You can just go ahead in MATLAB or Python and try different readouts, different type of sequences, and test them at the scanner. And also it's cross-software version and cross-platform also. The sequence I have developed, I have tested it in different software versions, specifically Siemens. So I have tested in BB17, B12, XA30. So yeah, it is indeed true that you can take the same sequence and use it at different software versions. The reconstruction package, Julia again, MRI Reco. As I said before, it has a fast NUFFT. It also has different solvers, such as the conjugate gradient sense reconstruction. And there is also a sub-package that allows you to compute the sensitivity maps using Spirit. So basically, MRI Reco has everything needed to, also B-naught correction actually, everything needed to reconstruct the spiral images. These are the three main challenges I have seen when trying to get good spiral images. And the first one is the non-Cartesian reconstruction. We are also more susceptible to off-resonance effects. So if we have more off-resonance artifacts when we do spirals, and also since we are only using one readout, during the readout, we use the two X and Y readouts, for example, so we are a bit more susceptible to trajectory deviations. I will explain a bit more the challenge number one, which is non-Cartesian reconstruction. Here we can take a look at a very simple, the typical signal model, where we have the signal, the K-space data that we acquired. In this case, I'm taking a look at two shots, spiral out data. We have the magnetization, which is the object we want to recover. And we have the K-space trajectory, right? So this will be the very simple signal model. If we get this type of spiral data, in this case with a 3 undersampling in plane, and we just perform NUFFT, this is what we get. So this will be just gridding of undersampled spiral data. And as you can see, the aliasing artifacts look very different and they're all over the place. Again, the main limitation of this is that making one reconstruction like this requires to use a NOFT, which is more computationally expensive than FFT, but MRE recon can help a bit and make this process faster. But of course, if we are undersampling our data, we would like to make use of, we would like to do parallel imaging to be able to recover and yeah, get rid of these artifacts that we get from undersampling. So if we add to our signal model the sensitivity maps, in this case computed from Spirit, we can then do the reconstruction with the NOFT, and we could use a conjugate gradient sense algorithm, and we arrive at something like this. So this will be sense reconstruction of 2 shots, or do a shot undersampled by 3 spiral data, right? And as you can see, well, we do get rid of most of the undersampling artifacts by making use of non-Cartesian sense reconstruction. But this image is still very bad, right? It's very blurry. It's not something we would like to use. And specifically, it doesn't have the resolution that we were targeting in this case, which was 0.6 isotropic. Then that brings us to the second challenge, which is of resonance artifacts. So that image I showed before, as I said, it had a lot of resonance artifacts. But if we go ahead and include into our signal model a BNOT map, we can then reconstruct the data, making use of the NUFFT, conjugate gradient sense. And if we include this BNOT correction, we come to this image on the right, which now is way better. It's something good, I think, so something we could work with. Again, from the previous slides, we saw that there were so many of resonance effects, blurring mostly, and we can make use of the multi-frequency interpolation approach for of resonance correction, or the time-segmented of resonance correction. This data use multi-frequency interpolation for the resonance correction. Then trajectory deviations, in the cases before, I was using the nominal trajectory, which, as you can see from this figure on the top, the nominal trajectory and the GIRF predicted trajectory look very similar. So I didn't see a huge difference when making use of this GIRF predicted trajectory compared to the nominal trajectory. But yeah, then we could, instead of use the nominal trajectory, we could use either the GIRF predicted trajectory or the measured trajectory with the scope. And in this case, we should get even a better image. So we will be using the actual trajectory that the scanner is being played, and this should improve the image quality.
Alejandro, can I ask you? So based on the maybe the field map, it looks like a 9.4 Tesla dataset. So you had scope available at 70 and 9.4. Is that right?
The what, sorry?
The scope system, or like you're not specifying if you use the GIRF or the scope. This looks like 9.4, and you have a scope in Maastricht at 9.4. Or did you use scope for 70 and 9.4, or?
No, actually, yeah, that's a good point indeed. So for the data we show later, we did measure the trajectory with the scope system at 70. So we did have a 70 in Maastricht scope system for 70, but not at 9.4. And that's actually the reason why for this 9.4 data set, we looked at the GIRF trajectory. Yes, we characterize the gradient with GIRF. Yes, indeed.
Maybe while I'm talking already, I had another question. So Denise, she always, like, you have a stack of spiral, right? And then you do the undersampling, but for the undersampling in the C direction, you can also have these blips in there, like Denise had in hers, right? Do you have them that you kind of have different kind of levels of spirals, and then you jump between them with the Kuiper blips, or is it all planar for you?
Yeah, so these images I'm showing, I was not doing through plane undersampling, so it was fully sampled in the partition direction. But some of the data I will show later, that I acquired later on, there I did do through plane undersampling. And one of the things actually is you could also rotate each plane. So, and that will also help you to cover a bit more of the K space. And for the blips, yes, but in that case, since it depends how long your readout is, of course. But what I did is I'll show later. So there was a data set that I got with 3 shots, very like high resolution, 0.5 isotropic. And in that case, one of the shots I did use them to cover, like to go to blip. So I was doing 2 shots and then I blipped, and then the 3rd shot was in between the undersampling data. So that was, I think that's as similar as it gets to CAIP for spiral, and it does improve a lot. Like your aliasing gets a spread also in the partition direction.
Makes sense. Thanks.
Yeah, thank you, Rizzo. So yeah, once you move from, like, you use different shots, it gives you also a bit of flexibility on how to blip up and down. With a single shot, it gets tricky, especially because of the long readout. Thank you, Rizzo. So yeah, then once again, you can get your trajectory. You can measure it with a scope if you have a system for this, or you can use the curve predicted trajectory. And that's it. I did not include any higher order effect field dynamics into the reconstruction, but that's something you could also include. But as far as I know from Lars Kasper work, it might not make a big difference to include higher order higher order field dynamics into the model. But you could do it, of course. Not with the current reconstruction. Yeah, you will have to modify the reconstruction. Okay, so now after showing you what is needed to get good spiral images, I will explain a bit more on the pipeline that I've been working on, that I've been putting together. So we start with the MATLAB toolbox of PulseSec, where we generate our all the sequence diagram. For the spiral design, I made use of the optimal gradient design algorithm. There is also this toolbox from Mickey Lustig's lab. So you can prescribe the trajectory you want to cover. You input that into this toolbox, and it will give you the gradient waveform that achieves that trajectory. And of course, there you input your gradient constraints, such as gradient amplitude and slew rate. Then, from PulseSec, you save a directory with different parameters, such as the field of view, resolution, flip angle, matrix size, all your undersampling parameters, as well as the spiral parameters. You also save the nominal trajectory. So also from PulseSec, you can easily get the case-based trajectory, and you can just save it into the MATLAB file that you can then use for the reconstruction, and also the sequence file. So this is the file that you will put in the scanner, and that it will be, that you will run in the scanner. The next step in this pipeline is to, go to the scanner, get the data. This will be the fMRI data, the spiral raw data. And for the sense reconstruction, and also to include the p-not correction, we also got a multi-echo GRE spiral acquisition, in this case, very highly segmented. So I was targeting 42 shots. So it's a very short readout. And it's fully sampled, of course. So then we cover the same area. We take this like preliminary pre-scan that is fully sampled, very highly segmented, and this way we can actually reconstruct it without having the sensitivity maps or anything else. The next step is to convert this raw data to ISMRMD file format. The main reason for this is because MRI-RECO at the moment can only read data from ISMRMD, so you cannot directly read the Siemens raw data. You convert both the fMRI data as well as your multi-echo GRE data into ISMRMD. The trajectory, you can either use the nominal trajectory, the curve predicted trajectory, or your measured trajectory. Then the next step will be to merge this raw data with the nominal trajectory or your trajectory. In this case, we also perform some door correction, dynamic of resonance correction, repetition by repetition. This was mostly to get rid of any phase offsets due to the scanner drift. So this was also an important step we implemented. And this is the multi-echo GRE data. In this case, you can just do reading with MRI record, and you acquire your, in this case, 3 different echoes at lower resolution. And then we use the package MRI coil sensitivities, also Julia, to get the sensitivity maps. And there's another package also, MRI field maps Julia, to get the field maps. So with this, now we have everything that we need to be able to reconstruct our data. Then these 3 different files are input into MRI record, where we perform the iterative image reconstruction, including using conjugate read and sense, as well as a static V-node correction. After you reconstruct your whole fMRI series, then you can use any of the tools you want for the analysis. And in this case, I use AFNI and FSL for the GLM. I have to say here that I've been mentioning how this is a slow process. So normally in this type of pipeline, I was exporting the raw data, the 30, 40 gigs of raw data of the fMRI run, and then the reconstruction was done offline overnight. So each volume, it depends, of course, on the resolution, the matrix size, but it was taking maybe 2 or 3 minutes to reconstruct. So that's one of the big limitations of this approach, that is a slow process. Then this pipeline that I just described, the first project or the first project that we used it for was for a stack of spiral VASO at 17. In this case, we implemented an SSSI VASO fMRI sequence. We use a simple stimuli of full screen checkerboard as well as finger tapping, covering of course, the motor cortex as well as the visual cortex in this direction. The resolution we used was 0.8 by 0.8 by 1 millimeter. And yeah, these are other parameters. Here we went for the shortest possible echo time, which in this case, it was 2.4 milliseconds. And we did single shot the spiral out. So here, one of our ideas of we were wondering how much bolt contamination we were gonna get at this very short echo time. So we were hoping that maybe at this short echo time, there will not be as much bolt contamination as you normally get for EPI, which in this case of VASO, we don't want to have bolt, right? So I don't know how familiar, I guess people are familiar here with VASO, but anyways, yeah, we don't want bolt in VASO contrast. We also acquired EPI for comparison. And as you can see, the parameters are very similar. So the TR, effective TR is shorter for spiral. The volume TR is not too different. But the main difference, of course, is on the echo time. With EPI, we could do 23 milliseconds echo time, and with the spiral 2.4 milliseconds. So that's the main difference and what we wanted to take a look at. These are a little bit of the results. So this, on the left, we can see the spiral data. And if we look to the bolt contrast, we see how there is a lot of bolt activation. So this shows us that even at this short echo time, there's a lot of bolt activation. And the reasoning for this is that you get a lot of bolt in the outside of the K-space in your higher frequencies. So anyways, for VASO, you do need to get this additional bolt volume to be able to correct for or remove this bolt contamination. Nevertheless, we did find an increase in TSNR. This is expected, of course, for the significantly shorter echo time. And we also saw a bit of higher C-scores compared to the EPI data. As I mentioned, there is a high bolt even at this very short echo time. We also found a little bit of like higher relative specificity. In this case, we segmented the gray matter and the white matter, and we looked at how many activation or how many active voxels were present in the gray matter as compared to the white matter for both 3D spiral and EPI. And if we do this exercise, there is a bit more active voxels in the gray matter when we do spiral versus EPI. But as you can maybe see from your screen, there is a lower effective resolution with the spiral data. So this is something, yeah, one of the limitations of spiral, that even after of single shot spiral, I will say, that even after doing all your corrections, the image appears to be more blurry compared to API anyways. But we also compute the layer profile for both spiral and API. And as you can see, also with the spiral, we get a similar layer profile compared to API, where for the volt contrast, it is more biased toward the CSF. That's what we expected. And the vaso contrast has a bump in the mid layers.
Alejandro, can I ask something here?
Yes,
you mentioned this NUFT part in your reconstruction, like the frequency drift, I guess. It's assume a zeroth order just frequency across time. Was this applied here as well? Or like, is this something that you only need when you have a head gradient where kind of there's more heat up, or when you at higher fields where there's more gradient magnet interaction? Or did you apply this always?
Yeah, actually I did apply it always, but when I started looking into this, it was specifically with this project because I did see an image degradation. So I was reconstructing all of the fMRI series, and I don't know, a volume that I reconstructed after 6 or 7 minutes of fMRI was having many more of resonance effect. It was more blurry compared to the first ones. So at the end, yes, I always apply this repetition door correction to all of the data, yes.
Gotcha. Also at 70 with the body gradient, you have these field drift problems. Okay.
Yes, indeed. Okay. So I don't know if that's a bit more related to the high duty cycle of the spirals, but we're acquiring, so that might make us. And I think in API, anyway, you always do this type of correction, right? You always get your.
It depends. Yeah, you can. Yeah, it depends on your API. Like I do it at the beginning of the scan, but for me it would be just motion in the phase encoding direction. It would not be blurring, I assume. If I do my navigators, my phase frequency only once. Okay.
Another question for you, Alejandro. So we are using spirals quite a bit as well. One of the things we run into, at least with multi-slice spiral, is we're kind of limited right now to about 20 slices, give or take, because of SAR. Because you can have a much shorter TR. Maybe with Vaso, because you have this long inversion time, maybe it's not such a big deal, but have you found that?
No, actually not. Indeed, for Vaso, that was not a problem. Actually, yeah, at some point I was trying different configurations and I did find a SAR problem, but I think that was actually because of the inversion. But I have been doing some both also at 9.4, at 70, and at 11.7. I'll show a little bit later. And I never got into any SAR issues.
But Alejandro, this is a 3D stack of spiral, right? So your flip angles are very small, are they?
Yes, exactly. That's what I also wanted to mention. Is 3D stack of spirals, gradient echo, and I'm using the Ernst angle. So I think, yeah, the flip angles that I didn't include there are not too high.
The gradient magnitude that you showed in one of the previous slides was kind of capped at 30 millitesla per meter. Was that kind of just as an introduction? Here you don't have a y-axis, or did you use the full nominal gradient of the system?
Indeed, that's a good question. Actually, I also did not mention that, but I was, often capping them at around 30 millitesla per meter. But the main reasoning for this is that, it's a good question. Here. Yeah, well, I had 20 something. I think at the end I was doing 30 millitesla per meter. And it's mostly because of the forbidden frequencies, which is, I think it's an open topic still for many spiral people. Maybe Ravi also you have some comments on this. But
well, MGH has a great tradition of quenching our magnet with pulse sequences. Just ask Birkin. There are multiple forbidden frequencies that need to be characterized. That, if you have there's acoustic resonances, and then there are also coupling to the magnet. Larry Wall's done quite a bit on the coupling to the magnet piece. Siemens does mostly, they lock out the acoustic resonances, but they don't necessarily lock out the gradient magnet interactions. So these are, yeah, sort of unknowns, but we run spirals up to 80 millitesla, but we have a head gradient and a different magnet than the whole body magnet. So
yeah,
so
because
we're usually, sorry, go ahead.
Does that mean that you kind of the spirals have all the frequencies in there? Are you just sweeping through the forbidden frequencies real quick, or do you include them in your trajectory calculation like Kaveh
You
does?
include them in the trajectory calculation.
Okay. And then you kind of you have these jumps in your spiral that you kind of
yeah, you're kind of, it's a mix of amplitude and slew rate limitations as you kind of go through the spirals. But you know, there is a fundamental, it's a chirp pulse basically. So you can calculate, we do the Fourier transform on the waveform every time, and we make sure that it's not hitting anything that we know about, but there are things we don't know about still.
Right.
So you do like for the spiral design, you do take into account this, and then you play with the gradient amplitude and the slew rate to make sure you don't hit those.
Correct.
Okay, yeah, because I at least at the moment, the only thing I was doing was making sure that the highest peak of the frequency spectrum was not in one of the forbidden frequencies. And one of the reasonings was that since we're sweeping very fast through all the frequencies, I don't know, that was a bit of our hypothesis that we're not hitting the same frequency over and over, but I don't know.
We don't know. I mean, you know, at a resonance frequency, you need very little power to actually excite the resonance. But we don't know how little that number is. You know, can we be 30 dB down from peak, and is that okay, or is that already still too much? You know, so these are things we don't understand. I mean, you can look at magnet Boiloff. That's not a very good measure. I mean, it's an average measure, but it's not a, you know, it doesn't tell you what happens at resonances and things like that. We've done the GERF. The GERF looks somewhat different than what Siemens has put as lockout frequencies in our scanner. So we're still trying to understand all this stuff.
Okay, yeah, it's good.
And we did a wave KP many years, well, not many years ago, 3-4 years ago. And at normal slew rates, it worked fine. And then when we went to SR 400, it quenched the magnet in 1 second. So that was a sequence we had worked with Birkin to develop. So, but it works fine on the Prisma. So, you know, who knows?
Okay, nice, interesting. So yeah, it's something also we should think about when designing the spirals.
Yeah,
making sure we don't hit those frequencies too much, or also do more investigation how it interacts. Okay, but yeah, in this case, I was playing with the slew rate and gradient amplitude to make sure that that highest peak of the frequency spectrum was not hitting one of the frequencies, forbidden frequencies, and that's the reasoning why I was not going to the highest available gradients and slew ranges. So yeah, then this was the first project, layer-fMRI at 70. There seems to be some small benefits of doing these spirals, but anyways, the downside of the reconstruction doesn't make it very appealing, let's say, to do spiral imaging instead of EPI for VASO. But there is a benefit, of course. There is a SNR benefit mostly and some small relative specificity. Then the next project that we work on, also building up on the experience we saw before, that there is a lot of bold even at very short echo time. So we're looking at options to perform both fMRI, in this case with spiral out. So spiral out imaging also, and we wanted to see what happens if we have a short echo time. Also, these findings were a bit explained by an abstract from Maria Engel that she introduced a concept called bold point spread function, where you basically take into account your trajectory to try to find the optimal echo time or to get the highest sensitivity, bold sensitivity. So we perform both point spread function simulations, including our data, our readouts. And in this case, the highest, these are the plots, the highest sensitivity, but we assume a T2 star of 22 milliseconds at 9.4. And our simulations show that the highest sensitivity will be achieved at 12 milliseconds. But we wanted to also see what happens if we go to shorter echo times, since the sensitivity doesn't seem to change too much when we use a 6 milliseconds versus a 12 milliseconds. So we perform different experiments, in this case, only visual experiments, doing a full screen checkerboard. We made use of dual shots spiral out readouts in this case, because when we tried to get single shot at 9.4, even after correction, the images were not very good. So this was because of the very long readout and the higher of resonances of the higher field. The nominal resolution we were targeting was 0.6 isotropic. And in this case, we were interleaving both of the echo times. So we were getting echo, well, one plane of 6 milliseconds, and then right after one plane of 12 milliseconds. Here, we wanted to try to make sure we had the same both weighting and just not introduce any other confounding effects. So that's why we try to interleave them. And yeah, well, that was the reasoning why we went for a smaller slab, and the TR was like 2.7 seconds. These are some of the results. So like as the simulations showed, we do have some high sensitivity at an echo time of 12 milliseconds, which is of course like 10 milliseconds shorter than the T2 star we were assumed. But also, if we have an echo time of 6 milliseconds, we also have very similar activation pattern between the 6 and 12 milliseconds. But the main difference, and that is very apparent here, is this apparent high activation in the superior sagittal sinus, which arises from when we have a shorter echo time. And we believe this is mostly inflow effects at this shorter echo time. But also we do have some 30% higher TSNR when we have the shorter echo time, and also a 4% higher temporal contrast to noise ratio when we have this shorter echo time. So after all this experiment was to first of all see the simulations of the bold point spread function, if they were giving us some good values. We could have, or actually we wanted to get more echo times to be able to have more data points. But the main limitation was that the scanner was going to stop working soon, so we could not do that much. But yeah, okay, we are able to do. It seems like we're able to do a spiral out both at this high field with a short echo time, with the benefit of the higher TSNR. So this is promising for both fMRI when we go to higher fields. Then after we performed this exercise at 9.4, we went ahead and scanned, in this case, only one subject at 11.7, mostly because, yeah, well, it's being difficult, or yeah, it takes time, let's say, to get approval to scan subjects at 11.7 Tesla. But we had the opportunity to test our bold sequence. The first thing we did, we performed the bold point spread function simulations for the specific readout we wanted to use here at 11.7. We also did a full screen checkerboard, also dual shot spiral out readouts. And yeah, this is the field of view we ended up using. And that we went for a more conservative resolution of 0.8 isotropic. For this, the bold point spread function simulation suggested that an echo time of 10 milliseconds will give us the highest sensitivity at 11.7. Here in the top right, you can see the images of the multi-echo GRE data. And we can see how at 11.7, even with this very, very short readout and highly segmented spirals, we do get some of resonance effects, even at a short echo time of 2.4 milliseconds. So this is something that should probably be optimized in the future if we want to get more data at 11.7, because at least this first echo should be free of resonance artifacts. And here we see a single volume and an example of the reconstruction, how when we don't do any of resonance correction, we see some of resonance artifacts, but after doing the multi-frequency interpolation of resonance correction, the image quality significantly improves. And well, the results are, again, since we only got one subject, we cannot say much about it, but we did get a lot of activation as we can see over here. This was a 7 minutes block design, 30 on, 30 off, so a simple block design. But anyways, we do see that very high TSNR, especially at the back of the brain. So yeah, the 11.7 does bring that boost in SNRs, which we saw here with this data. And we also acquired compute the layer profile in this area over here, and it looks as expected, right? So we have the bias towards the CSF as expected from both imaging. We were also a bit surprised here with the data we got because we really didn't know what to expect. It was the first time we were getting data at 11.7 with the spiral. And yeah, we were happy with the initial results. And as Renzo mentioned, this was the first layer results acquired at 11.7. So that was also nice to be part of. Then just before leaving Maastricht, I was trying to push a bit more the boundaries or trying to push more these sequences. And I prepared a sequence to do full brain at 0.8 isotropic. And yeah, also with the ballpoint spread function simulations, we got a echo time of 14 milliseconds, which again, maybe we could use a shorter echo time. And in this case, the undersampling was almost 10, was 9.9. So here I did 3.3 actually undersampling in the partition direction. And yeah, in this case, again, every plane is rotated to cover a bit more of the K-space area. The images do present quite some of resonance effects, so they are not the best images ever, but I think, again, also for the first attempt to this, it was fine, but the parameters probably need to be optimized a bit more if we would like to do this full brain with this sequence. Also, the TR was quite long, 6.8 seconds, which, yeah, maybe should be optimized. But it was good to see that the same sequence can be used to higher coverage and undersampling in the partition direction. Then during that session, I also tried 0.5 isotropic. In this case, I tried triple shot. So this is triple shot to spiral out. In this case, a slab of 24 millimeters and an echo time of 14 milliseconds. And with a 6.6 undersampling. So I don't have a figure here, but here is what I was explaining earlier, how I was doing 2 shots in the same plane, and then the third shot, I was blipping up. So that way it's similar to Kaipi way of doing spirals. That does help a lot in getting decent images with this higher undersampling. The TSNR is not too high as expected from this high resolution. This is an image from the center slide, so I think it doesn't have a lot of resonance effects. It does appear to be maybe closer to 0.5 isotropic, even with these spiral readouts, mostly because of the shorter readout per shot. And there is also some bold activation. This was also at 8 minutes run. So of course we need to acquire more data, but seems a bit promising. But also we do see quite some aliasing artifacts in the lower and upper slices, as we see here. And I think I know the reason for this is I was trying to implement the phase oversampling in the partition direction, and I think I had something wrong there. So this is something that can potentially be fixed, and we should be able to get some nice images without any aliasing artifacts in the partition direction. So yeah, that was the last project I worked before leaving Maastricht. So just to conclude, we developed and we put together a cross-platform and flexible sequence implementation with stack of spiral readouts for fMRI. We made use of open source tools also for the reconstruction, and including the V-node correction, torque correction. Also, you can make use of the GIRF or measure trajectory. We successfully used this sequence at different scanners and different sites. And I believe segmented spirals, especially segmented dual spiral out, or is very promising for high resolution fMRI at ultra high fields, because it will give us a boost in SNR, in TSNR. We also demonstrated that we can use a shorter echo time to get significant bolt activation. And yeah, of course, the higher we go in field, the T2 star becomes shorter. So we do need to have a shorter echo time, which I think spiral might bring that benefit compared to EPI. But the main limitation, again, is the slow of resonance reconstruction. That has to be done over. Some possible future directions is to maybe take a look at the PTX implementation of PulseSec, which I believe there's people working on this, so we could take a look at. Also, we already have some FID navigators into the sequence, and this navigator data will also potentially be used to do some retrospective motion correction or dynamic of resonance correction. This is some work that was done by Tess Wallace, so this is something we could also take a look at. And also, well, if you have a scope camera, NeuroCam, for example, we could think of doing concurrent field monitoring. So yes, this is all. Thank you for your attention.
Thanks, Alejandro. We are almost at the full hour, but I do want to give the opportunity to ask a few questions if anybody has some.
Yeah, I have one question. Long time ago, we used to do EPI, segmented EPI, center out. So that is very much like your spiral out in terms of TE and distortions and things like that. But we haven't done this in probably 20 years. I wonder if you've actually compared, center out EPI versus, center out spiral, basically, because you also get a significant reduction in artifact. When you do that, you still get lots of bold, as you've shown with the spiral as well.
Mm-hmm. No, actually, no, I haven't. So that was one of the things for the first project. We tried to compare with EPI, but of course it was challenging because there are just different type of acquisitions. And then moving forward, we decided to focus on the spiral, like try to isolate a bit spiral, find the benefits of spirals. But of course, if at some point people want to, like if we want people to use more spirals, indeed, we do need to compare it. But no, I haven't taken a look at this type of center on EPI. Because what do you think, Ravi? Do you think like it will be the same as what I show now, or there's...
It might be similar. I mean, arguably, spiral still has better theoretical advantages because you're spreading the G factor noise in multiple dimensions, basically, in a kind of symmetric manner, unlike EPI. The big problem, with spiral is the reconstruction. And we use full model reconstruction using the scope trajectories and everything else. And regular EPI, you can reconstruct 100 images a second. Spiral, you can't even come close. And if you use the full model reconstruction, you could be waiting a few days for your 600 volume acquisition. Maybe cognitive neuroscientists, maybe they don't care. Certainly clinically, no radiologist is going to wait that long for data.
No, definitely. Yeah, I agree. Then the reconstruction is the main
so I
point.
think we need better ways. I have this argument with my colleague Corey Barron all the time because he's written this fabulous toolbox that we use, starting from BART, but much more advanced than BART. And he says, computers get faster every year, but if you do the math, it's going to take 50 years before computers can get fast enough to do what we want them to do. So I mean, maybe you need other deep learning. Compressed sensing is very slow for the recons. Deep learning, maybe it'll be better. I don't know. I mean, Mitra, is here. She's working on that for her postdoc, so we'll see. But yeah, it is slow. This is the problem.
Yeah, I agree totally. I'll see Mitra whenever there's something out there that we could all use.
Maybe a question in another direction. A couple of years ago, Bruceman, they showed these amazing structural spiral data. It was kind of very high resolution multi-echo GRE, and you use multi-echo GRE with a kind of highly segmented spiral as well as your reference data. But have you ever thought about kind of optimizing structural imaging? Because ultimately it should be more efficient and more flexible than Flash as well. And with the inversion pulse, you can even do kind of a spiral MP2 range if you want or something. It should also be more efficient at the end and give you extra degrees of freedom.
Yeah, well, no. Short answer, no, I have not looked into it. But indeed, I think there are many more benefits. And I don't know, I think I saw at some point some spirals MP2 range or MP range images, but I don't know. I think there might be people doing this. Maybe Flash, as you said, also Divya did ask last time about this, and I don't know. Maybe we could implement some Flash with highly segmented response.
It is the full hour now. If there are no further questions, then let me remind you that in 2 weeks, Saskia Bollmann is presenting on machine learning vessel segmentation in high resolution, I think, time of flight and multi-echo GRE data. So I hope I see you then. Bye-bye.
Thank you. Bye, guys.
Alejandro.